Hello everyone, welcome to my channel Progressive Physics Learning Profile. We are discussing class 12 chapter electric charges and fields. In that today I will discuss a subtopic called electric flux, Gauss law and its applications. So first we will define what is electric flux. As we already defined electric field lines, number of electric field lines passing through given cross sectional area given cross sectional area, we'll call that as electric flux. If suppose we are given like this, there is an electric field, uniform electric field is directed along positive x-axis. In this, if suppose we are having any cross sectional area, for area we have to take area vector perpendicular to its surface. If the angle between electric field vector and area vector will represent with S and electric field vector I will represent with E. The angle between them is theta, and the electric flux will represent with this symbol, that is given as E bar dot S bar, or for any small infinitesimal areas it will be integration of E bar dot ds bar, or this we can write like this Es cos theta. We will have some questions based on this dot product as well as this also. If theta is equal to 0, then cos 0 it will be 1, so that flux will take a positive value. That positive value will be E into S. That means for any surface like this, if this is our area vector and if that electric field is also in the same direction, then only that angle between area vector and electric field vector is 0. So that we can say like this, field lines are leaving the surface. So positive flux means field lines leave the surface. Field lines are leaving the surface or leaves the surface, then only we have to take that flux as positive. And similarly, if theta is 90 degrees, then cos 90, which is 0, so that flux linked with that surface will be 0. That means if suppose area vector is like this, and as electric field vector is in this direction, so that this is our electric field vector, this is our area vector, so angle between them is 90 degrees. In that case, flux linked with that surface is 0, or there is no flux linkage, we can say like that. And now if theta is 180 degrees, then cos 180, which is minus 1, so that electric flux will be equal to minus E into S. So if you are having a surface like this, for this electric field vector, if suppose that is in this direction, that means electric field vector is entering like this. If I am considering that area vector on the other surface, so this will be area vector, this is electric field vector. So then that flux will be negative. So if field lines are entering into the surface, so if the field lines are entering, we have to take that field flux as negative. Field lines entering the surface, then we can take that flux as negative. And as we are having electric field units as Newton per Coulomb, so units for electric field will be Newton meter square per Coulomb, and dimensional formula we can write the dimensional formula for electric flux like this. As the units are Newton means it will be ml t power of minus 2, meter square means L square, by Coulomb means ampere into time. So that this will be equal to m L cube t power of minus 3 a power of minus 1. This is corresponding dimensional formula for electric flux. So once we know this, what kind of questions you can expect means, I'll give you two examples here. Just look at these two examples. If suppose you are given like this, electric field is given as 4 Newton per Coulomb and area vector is given as 2 meter square and plane of the surface is making an angle 30 degrees with electric field. Then find flux, they will ask. If they ask a question like this, then we can, this is our surface, for that surface, this is our area vector, and if suppose field is inclined like this is electric field vector, this is area vector, and they gave one statement like this, making an angle, plane of the surface is making an angle 30 degrees, so that this will make an angle of 60 degrees. So flux will be equal to E A cos 60. Cos 60 is 1 by 2. So 4 into 2 into 1 by 2, or that will be equal to 4 Newton meter square per Coulomb. This kind of questions you can expect. And the second example will be like this. Electric field in a region is given as 2 I cap plus 3 j cap minus 4 k cap, and area vector is given as I cap plus j cap. Then they will ask you what is flux through that given surface. Then we have to go with this dot product E bar dot S bar, that will be equal to 2 I cap plus 3 j cap minus 4 k cap dot I cap plus j cap. So I dot I, it will be 1 and j dot j also it will be 1. So we'll have 2 plus 3, which is equal to 5 Newton meter square per Coulomb. So this kind of questions you can expect based on this electric flux. And we are having one more point like this. As flux entering is taken as positive, flux leaving is taken as positive, and flux entering is taken as negative. We are having one interesting note point. Based on this note point, we are having some applications like this. If suppose there is a uniform electric field like this, in this electric field region, if suppose any surface is placed like this, number of field lines entering is equal to number of field lines leaving. So flux entering will be equal to magnitude wise flux leaving, but total flux linked with the surface. As one is entering, we have to take that as negative, leaving, we have to take that as positive. So total flux linked with this is 0. So net flux linked with the surface, net flux linked with the surface is 0. But if they ask like this, what is maximum flux linked? Then that cross sectional area we have to take. This maximum cross sectional area is A. If suppose its cross sectional area is A, So that maximum flux linked will be equal to E into A, or that will be, if it is circular shape, we can take E into pi r square. It depends upon nature of the cross section. If it is a square plate, you will get E into A square like that. So now just look at this examples based on this note point. If we are given like this, there is a uniform electric field that is directed along positive x-axis, and they will give you like this. In that region, there is a uniform sphere is placed, or else they may give you like this. A cube of side length A is placed, or else they may give you like this. Suppose that uniform electric field is in this direction, a cone of height h and base radius r is placed. So if they gave like this, then what is net flux linked with all these surfaces means it will be 0, but maximum flux linked with this sphere if they ask, so that maximum cross sectional area will be a circle, so that E into pi r square, where r is the radius of that sphere, and here for a cube its cross sectional area will be a square, so that for that flux linked will be E into A square, where A is the side length, and for a cone the maximum cross sectional area will have a shape of a triangle. This cone height is given as h, and if base radius is r, its diameter will be 2r, so that flux will be equal to E into area. That area will be equal to, as it is a triangle, half base into height, which is ERH. So you can expect some questions like this. What is maximum flux linked with that surface, they will ask. So you have to answer like this. And one more example is based on this particular model. Just look at this example. If suppose they gave like this, there is a uniform electric field, and in this region a hemispherical bowl is placed. It will have a plane surface. If the plane surface is having circular shape, its radius is r. It was given like that. Suppose the radius is r, and they will ask you like this: what is flux linked with the curved surface of this hemisphere? Flux linked with curved surface of the hemisphere. If they ask like this: what is flux linked with the curved surface of the hemisphere? Total flux linked will be 0. That will be flux linked with the plane surface plus flux linked with the curved surface, which is equal to 0. So flux linked with the curved surface will be equal to minus of flux linked with the plane surface. As that field lines are entering, flux linked with the plane surface will be negative, so that it will be minus E into A, or that will be minus of minus plus E into A, that is having circle in shape. So E into pi r square. So this kind of questions also you can expect based on electric flux associated with any given curved surface. So you can follow the same method basing on that given shape. Now, with the knowledge of this, we'll define Gauss law. It is defined as electric flux through any given closed surface is 1 by epsilon naught times charge enclosed by the surface. Charge enclosed by the surface. And if suppose we are having any arbitrary closed surface like this, and if you are having some charges Q1, Q2, Q3, all the charges are inside and one charge is outside, then this electric flux through any closed surface, integration of E bar dot ds bar, that will be equal to Q enclosed by epsilon naught. This is our actual statement of Gauss law. And here in this case, Q enclosed will be equal to Q1 plus Q2 plus Q3. So that as Q4 is outside, we need not to consider that. But electric field wise, we have to consider all the force fields due to all the charges or field due to all the charges. Q1 plus Q2 plus Q3 by epsilon naught. If any one of them is negative, we have to consider that negative charge also. So here I'll give one simple example based on this. That first example will be like this. If suppose a surface is enclosing a dipole, find net flux through a surface that encloses a dipole. If you are given like this, so as dipole is nothing but we are having a positive charge and negative charge separated by a fixed distance. So total charge enclosed will be equal to 0 and hence flux will be equal to 0. And another interesting note point is that charge enclosed by the surface we are considering as the net flux is 1 by epsilon naught times the charge enclosed by the surface. So that flux linked is independent of shape of the surface. Independent of shape of the surface that is enclosing the charge. If we know this point, we are having some simple examples based on this. Just look at this first example. If you are given like this, there is a cube or there is a sphere or there is a cylinder and there is a charge placed inside this. The charge value is Q. So what is flux linked with this cube or sphere or this cylinder means is independent of the shape. So flux linked will be Q by epsilon naught. So this is our first point, and the second point, for this cube we'll have like this. For cube we are having 6 faces. If they ask like this, flux linked with each face of the cube, each face of the cube if they ask, so it will be q by 6 epsilon naught. And similarly, just look at this. If they gave like this, there is a cube and if a charge is placed on one face of the cube, or if you are given a hemisphere, or if you are given a cylinder, if you are given charges placed on the base of this hemisphere or else here, then we have to construct an imaginary Gaussian surface which is identical to this original surface. Then this cuboid will observe a cuboid. This encloses this charge q, so that as total flux linked with the cuboid is q by epsilon naught. Now flux linked with this cube will be q by 2 epsilon naught. And similarly we have to construct another hemisphere so that this charge will be enclosed by this complete sphere, so that flux through this hemisphere, as total flux linked is q by epsilon naught, flux linked with this hemisphere will be q by 2 epsilon naught. And here also we have to construct one cylinder, and as total flux linked is q by epsilon naught, here flux linked with this will be q by 2 epsilon naught. This kind of questions also you can expect. And then after this, one more example will be there like this. Just look at this. If you are given like this, there is a cube and charge is placed at one corner of the cube. Charge is placed at one corner of the cube like this. What is flux linked with this cube, they will ask. To close that corner, we have to construct a Gaussian surface such that to close that we need another 7 cubes. We need another 7 cubes, then only we can close that corner. So that flux linked with this one cube. So flux linked with one cube will be equal to q by 8 epsilon naught, because we need another 7 cubes. Apart from this original cube, we need another 7 cubes to close that corner. So flux linked with this cube will be q by 8 epsilon naught. If you observe that those corners or those faces which are meeting at that corner, with them there is no flux linkage, because field lines are parallel to the surface, means perpendicular to the area. So flux linked with the corners meeting at that point where charge is placed is 0, because field lines are parallel to the surface. That means area vector is perpendicular. So if we are having 3 corners which are meeting here, the remaining faces will share this flux. So that flux linked with the remaining three phases. Each of the remaining phase is Q by 24 epsilon naught. You can expect some questions based on this, and one more simple example I can give like this. So there is a cube and if they gave like this a rod of linear charge density lambda is placed along body diagonal of the cube, then find flux linked with that. Body diagonal means if I consider this as our first point, this as our second point, if I placed a rod like this, that gives you body diagonal. So what is body diagonal length means it will be root 3a body diagonal length is root 3a if a is the side length, then charge enclosed will be linear charge density into length root 3a, so that flux linked will be charge enclosed by epsilon naught, so that will be root 3 lambda a by epsilon naught. So you can expect some questions like this also. Or else one more example I can give like this. Just look at this example. If you are given there is a sphere and a wire of linear charge density is passing through one of the chord of the sphere such that this radius vector is making an angle 60 degrees. This is radius, let this be x. Then if linear charge density lambda is given, linear charge density lambda is given, so that they will ask you what is flux linked with the sphere. Flux linked with the sphere. For that we have to find this x value. If that is x, this will also be x. So that 2x we have to find. For that we will use sine function. Sine 60 is equal to opposite side by hypotenuse. So that x is equal to r sine 60, whose value is root 3 by 2. So that this will be root 3 by 2 r. So total length will be equal to 2x, or that will be equal to root 3 r, and hence total flux linked will be equal to charge enclosed by epsilon naught, which is linear charge density into length by epsilon naught, or that will be equal to root 3 lambda r by epsilon naught. So you can expect some questions like this based on identifying electric flux through any closed surface. Here one more note point is there like this based on solid angle concept. So I hope you all remember this solid angle. If any surface is there, the three-dimensional angle subtended by this surface, we'll call that as solid angle will represent with ohm or omega, and if suppose theta is the semi-vertex angle, here this is solid angle, then theta is known as semi-vertex angle. Then relation between these two is 2 pi into 1 minus cos theta. Flux through any given solid angle is given as q by 2 epsilon naught into 1 minus cos theta, where the q is the charge enclosed by that surface. So this is one interesting area, particularly in JE. You can expect some questions based on this, sometimes in NEET level also. I'll give some examples based on this. If suppose you are given like this, there is a jar. This jar radius is r, and at a depth h, a charge q is placed, and that depth h is given as 1 by root 3 r. So then definitely it will, this surface will subtend some solid angle here. To find that solid angle, we have to find this semi-vertex angle theta. For that, I'll take trigonometric function tan theta, that will be equal to r by h, r by root 3. So that this will be root 3, that will be, that implies theta is equal to 60 degrees. Then flux through this cap will be equal to q by 2 epsilon naught into 1 minus cos 60. Cos 60 is 1 by 2. So that this will be q by 4 epsilon naught. If suppose they asked flux for flux through curved surface, then total flux minus flux through that cap we can subtract. So that this will be q by epsilon naught minus q by 4 epsilon naught, that will be 3q by 4 epsilon naught. You can expect some questions like this. And one more example I'll give you based on this model. Just look at this example. If you are given like this, there is a cylinder, and this cylinder length is 2r, where r is the radius of the cylinder, and a charge is placed at the center. So definitely we can observe two cones will be observed, and as their center to center distance is, for this surface to surface it is 2r, means from the center it will be r, so that this angle will be 45 degrees. So now we are having two caps, so flux through that caps will be equal to 2 times q by 2 epsilon naught into 1 minus cos theta, or this 2 gets cancelled. We are having q by epsilon naught into 1 minus theta is 45, means 1 by root 2. This is flux through that end caps. And if they asked for flux through this curved surface, flux through the curved surface will be equal to total flux minus flux through that caps. Total flux is q by epsilon naught minus q by epsilon naught plus q by root 2 epsilon naught. So q by epsilon naught gets cancelled. We'll get q by root 2 epsilon naught, that is flux linked with the curved surface. So these kind of questions you can expect based on Gauss law. That's it for this video. I hope you all understand all the points what I discussed. Have a great time. Please subscribe and share progressive physics learning profile. Have a great time.